Objective 1.3, complex numbers. In this lesson, we want to define and identify complex numbers. We want to be able to plot complex numbers in a complex plane. We want to perform operations with complex numbers, and we want to find the absolute value of a complex number. So if we look at the vocabulary, first we see the definition of what I means. I is what we use for an imaginary unit, and it's defined as the square root of -1. A complex number is written in standard form if it's in the form a plus bi. The a and the b are real numbers, and the I is what we just identified. It's the square root of -1. If b is not equal to 0, then the a plus bi is called an imaginary number. If the a is 0 but the b is not, then we have what's called a pure imaginary number, because we don't have that a, we just have the bi part. The sum of complex numbers, so you see a plus bi, that's one complex number, plus a second complex number of c plus di, simply means that we're going to rearrange things, and we're going to add the real parts together, and we're going to add the imaginary parts together. And you're going to see examples of that in just a minute. Same with the difference of complex numbers. We're going to kind of rearrange things, but we need to make sure that we're subtracting both the real parts and the imaginary parts. A complex plane looks like a normal graph, except that the horizontal axis is called the real axis instead of being the x-axis. And the vertical axis, instead of being y, is the imaginary axis. So again, we look at the standard form of the complex number, we identify the real part and the imaginary part, and that's what we use to graph a complex number on a complex plane. And a unique feature of complex numbers is that we have things called complex conjugates. And a complex conjugate is simply the same two terms, but in one case it's being added, and the other case it's being subtracted. These are not opposites of each other. If it was an opposite, the a would also be opposite, and that's not happening. So if I have something in the form of a plus bi, the complex conjugate is simply a minus bi. And the nice thing about that is that the product of complex conjugates always ends up giving you a real number. And again, you'll see why in just a minute. So let's talk about what complex numbers are. You see here numbers, categories of numbers that you are probably familiar with. We have counting numbers, which are exactly what they sound like. They're the numbers that we use to count things. So 1, 2, 3, 4, 5, all the way on up. If we take counting numbers and add 0 to it, then we have the category of whole numbers. So you notice that the whole numbers includes the counting numbers because they're inside of the whole number box, but then it also includes 0. Now if we take all of the whole numbers and add to that their opposites, then we have the category of integers. Take all of the integers, add rational numbers to it, add fractions and decimals to it, we have rational numbers. The decimals need to be decimals that are either terminating or are repeating with a certain pattern. Another way of defining that is it's a decimal that could be written in a fraction form. Okay? So again, all of those rational numbers, those fractions and decimals, are in addition to the integers, the whole numbers, because they're all inside of each other's boxes. And then we have a group called the irrational numbers, which are those that as decimals, they never terminate and they never have a repeating sequence that keeps repeating. There's no pattern to it. So things like pi, e, square root of 2, negative square root of 5, those are examples of that. And so all of those together make up the category of numbers that we call the real numbers. And normally those are the types of numbers that we use when we're working out math problems. But it's not the biggest category of numbers we can have. Real numbers are simply a part of a larger category called the complex numbers. So the real numbers that you see there on the left-hand side are all numbers where b was 0. So those are all just various types of a's. But if b is not 0, then we add on the right side of our box. So if b is not 0 but a is 0, we have the category called pure imaginary numbers. If a or b are not 0, then we just have what we call imaginary numbers. And those, along with the real numbers, make up the entire category of what we call complex numbers. And complex numbers always have a standard form of a plus bi. So we need to be able to use these complex numbers because sometimes we need to go farther than just real numbers allow us to go. And so the key to the complex numbers is the I, which we just defined a minute ago as being equal to the square root of -1. The thing to understand about I is that it is not a variable. It represents a value. Granted, it's not an easy value to get your head around, but it represents the square root of -1. Just like if I use this symbol, we know that represents a value approximately 3.14. Okay, so it's not a variable. What makes that a little bit tricky is the fact that it oftentimes acts like a variable. It acts like we would expect a variable to act. But we have to remember it's not just a variable, it actually represents a particular value, and that particular value is the square root of -1. Now it's nice to have this I because now we can deal with negatives inside of the radical. Without complex numbers, anytime we get a negative inside of the square root, we always say we can't do that. Now we can do that. We can deal with that negative. So if I have something like the square root of -16, it's like saying I have the square root of the -1 times the square root of 16. Well, the square root of -1 is where I comes from. The square root of 16 is where we get 4, and so we end up with an answer of 4i. Okay? And so we can do that anytime now that we have a negative inside of a radical. We can deal with the negative by making it I, and then we can deal with the square root of the rest of the number by simplifying it as much as we can. So the square root of -9 would be 3i. The square root of -100 would be 10i. The other thing that's interesting about this is because we have an equation that says I is equal to the square root of -1, if we square both sides of that equation, then we end up with an equation that says I squared equals -1. Not the square root of -1, just -1. And that can be a very handy little piece of information that we can use here in just a minute. So, complex numbers in standard form are in this a plus bi form. The a is what we call the real part. The b is what we call the imaginary part. And if we're trying to graph a complex number in a complex plane, then the ordered pair of a comma b is what we're actually graphing. So let's start there. Let's plot complex numbers. So when we have the complex number 2 minus 3i, we identify that the real part is the 2 and the imaginary part is the negative 3. So we're going to be plotting the ordered pair 2, negative 3. But notice, as we stated in the definition, that my horizontal axis here is not labeled as x now, it's labeled as the real axis. And my vertical axis here is not labeled as y, it's labeled as imaginary. So when I say I'm going to negative 3, it's 2 in the real axis direction and then negative 3 in the imaginary direction, which matches up with where the 2 and negative 3 came from. Okay, in the next example I've got negative 3 plus 2i. So negative 3 is my real part, the positive 2 is my imaginary part. Notice we're not using the I, it's just the B. And so negative 3, positive 2 puts us over in the second quadrant. And then finally we have 4i. Since 4i only has an imaginary part, that would be a number that would stay on the imaginary axis and would have an ordered pair of 0, 4. Alright, so why don't you try some? You have a complex plane there on your note sheet. Go ahead and pause the video for a moment while you plot 4 plus 2i, negative 1 minus 3i, and negative 6i on your complex plane. Alright, so here's where you should have plotted your points. A would have been at 4, 2 in the first quadrant. B would have an ordered pair of negative 1, negative 3, which would be down in the third quadrant. And C would have an ordered pair of 0, negative 6, which would be on the negative imaginary axis. Alright, now, because we have complex numbers, we need to be able to do operations with them. So we're going to start with some adding and subtracting. And this is pretty simple, and this is where sometimes it's easy to forget that I represents a number, because what we're going to do looks a lot like what you would do if I was a variable. But what we're going to do is we're going to add the real parts together. So the 4 from here and the 3 from here get added together. And then we're going to add the imaginary parts together. So negative I from here with 2i from here, that's what's getting added together there. And those give us our real part here and our imaginary part here to give us the standard form of our answer. So this answer right here is in standard form because it has that a plus bi form to it. So it's really very simple to add and subtract complex numbers. We combine the real parts together, we combine the imaginary parts together, and we end up with an answer that's already in standard form. Okay, if we do the same with b, this time we're subtracting, so we have to make sure that we are distributing this negative or subtracting the negative. Let's do that again. Let me use a pen. There we go. So this negative needs to get distributed to both of these and turn it into addition. Or just make sure that when you are combining the 7 with the 1 that you are subtracting them. Okay, so what we see here is them changing this to addition and our second complex number to its opposite. And then when they took 7 with -1, they got 6, and -5i with +5i gave them 0i, so we just ended up with a real number answer of 6. Okay, so go ahead and try these two, an addition and a subtraction problem. Again, you can pause the video for a moment while you work these out and come back when you're ready to check. All right, so for part A, you should have gotten an answer of -1 plus 4i, and in part B, an answer of 6 minus 2i. Now, how about multiplying our complex numbers? Again, notice our directions say that we want our complex number to be in standard form for an answer. So, in the first case, if I distribute the 5i, I end up with -10i plus 5i squared. Now, that's a perfectly good result to my distribution, but it should not be my final answer because it's not in standard form. In standard form, I need a plus bi. There's no I squareds in my standard form. So this is where our little trick from a couple of slides ago comes in. We identified that I squared was equal to -1. So we're going to replace I squared with -1 and then simplify. And when we simplify, now we have the standard form of a complex number that we're looking for. -5 minus 10i. Our a is -5, our b is -10, and then we've got our I. So anytime you have an I squared come up in an answer, we need to replace I squared with -1 and then further simplify to get our standard form of the answer. In part B, we're going to FOIL to work things out. And again, you'll see that we've got a term with I squared in it. So we can combine our I terms, and then if we replace the I squared with -1, the -8 becomes +8, and then we can combine the real number parts to end up with 1 plus 18i. And again, that ends up giving us standard form for a final answer. Now in part C, you may notice that this is starting to look like one of the patterns we talked about last lesson. And if we FOIL it just to check it out, we can see that our -18i and our +18i cancel out. And if we replace the I squared with -1, then -9 becomes +9. So when we simplify all of this, we just end up with a real number answer of 45. And if you've been paying attention, you may notice that what we've just used here is what we defined a minute ago as complex conjugates. The two terms are the same, a 6 and a 3i, but in one case we're adding and in the other case we're subtracting. So these are complex conjugates of each other, and one of the things the definition said was that the product of complex conjugates would always give us just a real number. And that's proven to be true in part C. We just got a 45. So go ahead and try a few on your own. See if you can multiply these complex numbers together and make sure you're giving a final answer that's in standard form. All right, here's the answers you should end up with. For part A, you should get 2 minus 10i. In part B, we're again dealing with complex conjugates, so you just end up with an answer of 13. And in part C, you get an answer of negative 2 plus 26i. Now, what about dividing complex numbers? We've looked at adding, subtracting, and multiplying, but we also want to be able to divide. And oftentimes division is shown in a fraction form. So in part A, we're looking at the division of 7 minus 4i by 2 plus I. The key to this is to change the complex number in the denominator into just a real number. Well, we've just looked at some examples that did that. If we take our denominator times the complex conjugate, that should end up giving us a real number. But remember, if we're going to multiply the denominator by something, then we have to multiply the numerator by the same thing. So when I identify 2 minus I as being my complex conjugate, I have to make sure that I'm multiplying that on both the top and the bottom of my fraction. So now I can FOIL both the top and the bottom out. And what's nice is, again, on the bottom, the negative 2i and the positive 2i cancel out. The I squared becomes negative 1. And so everything in the bottom is just going to become 5. On the top, I can combine my I terms into negative 15i. I replace the I squared with negative 1 and combine my negative 4 to 14 so that I end up with 10. Now I just need to go one more step to simplify by dividing both the 10 and the 15i by 5. So I end up with a final answer in standard form of 2 minus 3i. That is the result of dividing 7 minus 4i by 2 plus I. If we take a look at another example, we're starting out by taking 6 and dividing it by 1 minus I. We need to identify the complex conjugate of the denominator, so that's going to be 1 plus I, and we multiply both the top and the bottom. Now on the top, I just need to distribute the 6 through the 1 plus I to get 6 plus 6i. In the denominator, if I FOIL, I recognize that the I and the negative I will cancel. The I squared will become negative 1, and I'll end up with 1 plus 1, which is simply 2. So now if I divide both the 6 and the 6i by 2, I end up with a final answer of 3 plus 3i. All right, your turn. See if you can work out this quotient where we're taking 5 plus 3i and dividing it by 1 minus 2i. If you're not sure how to do this, go back and rewatch that last section and then come back, try this out, and come back when you're ready to check. All right, so our complex conjugate of the denominator in this case is 1 plus 2i, so that's what we multiply on both the top and the bottom. We FOIL, we simplify, and we end up with negative 1 plus 13i over 5. Now negative 1 and 13 cannot be divided evenly by 5, but we still want to split up our a and our bi. So we would set up the fractions of negative 1/5 plus 13/5 I. All right, finally we want to talk about absolute value of complex numbers. Just like with real numbers, absolute value still means distance from 0. So when we're talking about 2 minus 3i, we know that that point is at 2, negative 3. So we saw that in one of our first examples. But now we want to know how far is that point from 0, which in this case would be the origin, 0, 0. So absolute value is still the distance from 0, and we get that by taking the square root of a squared plus b squared. It's really just an equation that comes from the Pythagorean theorem. Now notice it is just the b that's being squared. There is no I in this. You're only using the a and the b values to work this out. So in the first example with 2 minus 3i, I would take 2 squared plus negative 3 squared and then square root the entire thing. That would be a 4 plus 9, which would give me 13. So the distance from the 2, negative 3 point to the 0, 0 point is a square root of 13. If I work out for b, I would be taking negative 3 squared plus 2 squared and square rooting that, which just happens to also give me square root of 13. So the distance from my green point to the origin is a square root of 13 distance. For 4i, since it's right on the axis, I could just count the boxes from the blue point to the origin, and that would give me a distance of 4. But if you want to see it algebraically, it still works out the same. I would be using 0 as my a in this case, with 4 as my b. I end up with the square root of 16, which is simply 4. All right, last example. Go ahead and try to find the absolute values of each of these complex numbers, and then come back to check and to wrap up the lesson. All right, so if you set up the square root of a squared plus b squared in each of these cases, you would get a distance in part A of 5, distance in B would be 2, and our absolute value distance in C would be the square root of 26. All right, so lots of different things you can do with complex numbers. Hopefully you saw a lot of those the first time around, but in case there was anything you missed, this is just one more look at it. Now you're ready to go through the practice problems in Objective 1.3. Again, if you need any questions answered, seek out those resources that will help you to answer them, and don't forget to check the answers to your questions and your practice on Canvas when you're finished. All right, that's it for this lesson, guys. We'll see you next time.